Okay, so here's where we were last time. We were talking about integrals in polar coordinates. Whatever that means. So for the moment, really, all we know how to do is how to interpret polar coordinates as being a change of variables function. Right off the bat, that's a little bit of a twist in how we think about polar coordinates. Most people think about polar coordinates as a coordinate system. You know, you give me a point, this is a way of describing location. And I presented the idea last time when we were describing polar coordinates is think of polar coordinates as a function, where if you give me an r and a theta, I give you a point, right, based on certain formulas. Now I'm saying let's view this as, in fact, a change of variables function, which is a creative idea. Right? Okay, so we went through some details related to this last time. Namely, you can compute the stretching factor. Here it is. It's the absolute value of r. Oh, we hate absolute values. How can we work our way around that? Let's make a promise to always choose polar coordinates where r is never negative. Right? If we agree to that here and now, no negative r's, then we get to lose the absolute values. Stretching factor is now just r. How convenient. Right? So this is a good deal. It's a win-win scenario. You get to choose the polar coordinates you wanted to choose anyway. And in return, you also get to ignore the absolute values that you wanted to ignore anyway. Okay. Alrighty. And then we started talking about bounds. So this first example is deliberately sort of convenient one. So suppose we are looking at this domain right here. We talked through the details last time, and I argued that, well, this thing bounded as it is by, for example, these two lines, well, those are constant values of theta. So when I look at the pullback domain, they're constant values of theta. Namely, they're straight lines in the r theta plane, in the pullback world. Right? So similarly, these circles, concentric circles centered at the origin, that make up the other two edges of this little region, well, their polar equations are constant values of r. Constant values of r are straight lines over here in, again, the pullback world, r theta, the r theta plane. So the pullback domain here is a rectangle, everyone's favorite domain for a double integral. And so this is a really good change of variables function in this case. We've taken a highly undesirable domain and we've pulled it back to a wonderful domain. Okay. All right. In this new wonderful domain, of course, we slice it up in the usual way. Let's start with theta slices. Theta starts at, oh gosh, I'm sorry, my elbow again. Start with that slice, this value of theta, whatever theta 1 is. And then we keep doing theta slices until we get up to here. So theta goes from theta 1 to theta 2. Then, upon fixing some value of theta in there, right, the r slice starts here at that point. That point's on this curve. That curve has this equation. So there's my r bound, my inner lower bound. Okay. The last r slice is described by that point. That point's on this curve. That curve has this equation. There's my upper bound for that inner dr integral. Okay. All right. Now, I went through this process sort of inexplicably high detail, given that we know how to slice up rectangles. What you guys don't need me to remind you how to slice up rectangles, right? The reason I went through that is I want to point out that everything we just did over here, the whole slicing process there, and then the subsequent for a given slicing, for a given slice, you know, we slice up like this, all of that can be seen over here. To which you might respond, yeah, well, I like this picture better. Okay, fine, fair enough. But here's the thing about this original picture. This original picture is given, right? So you already have that picture. What I'm pointing out is that this whole slicing process over here, I don't even have to draw this picture in the first place, right? So let me show you what I'm talking about. Let's get explicit. Okay, so this, you know, theta starts there. That value of theta. Well, you can see that theta slice there. Constant values of theta, right? A constant value of theta in our theta world is a straight line perpendicular to the theta axis. Okay, well, a constant value of theta in xy world is, okay, it's not, there is no theta axis. It's not perpendicular to the theta axis. There is no theta axis. But it is nevertheless something that's really easy to understand. It's just a ray emanating out of the origin. So you can sort of re-visualize, this theta slicing process as instead just, well, there's my first theta slice. There are continuing theta slices, and there's my last theta slice. So first, last. Right? We don't really need the r theta picture in the first place. I mean, it's there. Let's not forget the whole idea here is that we're using the polar coordinates function as a change of variables function. It's a thing. I mean, it's there. It's over there. We want to know that that is ultimately, this is our new domain. Sure. I'm just pointing out that to find the bounds defining that new domain, you don't have to draw a picture of it. That's my observation here. Okay. All right. So likewise, proceeding, for a given theta slice, R starts there, R ends here. Okay. Well, I can see that over here just as well. There's a theta slice. The starting value of R is it's on that curve which has that equation. And the ending value of R, it's that point which is on that curve which has that equation. You can see everything you need to know right there in the XY plane. Okay. All right, so here's another example. Let's look at, let's see here, we have the first quadrant portion of the unit disk. This is our domain. That, right? And we've been down this road before, by the way, doing an integral on a domain like this in rectangular coordinates, and we know that square roots show up in the inner bounds, and that means square roots show up in your outer integrand. And yikes, right? I mean, that could be ugly. That's highly undesirable and makes life hard. So let's do this in polar coordinates. Again, I'm going to do this both ways. Let me first observe that the pullback domain. The pullback domain is this rectangle. Now, let's talk that through. How do I know it's that rectangle? Well, this curve here, that's r equals 1, which is that curve in r theta space. This curve, okay, what do I know about that curve? That curve is theta equals pi over 2. Right, you're going to want to say x equals 0. But in polar coordinates, this curve is theta equals pi over 2, where r goes from 0 to 1. Okay. That's that. Right. Similarly, let's see here, color choices. This curve, that's theta equals 0. R goes from 0 to 1. So you can see our domain starting to form. Now there is the little annoying matter of, what about this big opening here? Where does this all end? Well, notice that this entire edge here is r equals 0. That entire edge in polar coordinates collapses down to that single point. Right. So this is our new pullback domain. Is this right here? And so it's a rectangle, and you can again just look at the slices, constant values of this, that, and the other thing.
For the X and Y one, there's no corners or anything, there's no problem with slicing that up, right?
Yeah, this isn't a corner situation. This is I don't like square roots situation. Yeah, so that equation in rectangular coordinates, if you solve for x in terms of y or y in terms of x, as you will have to in rectangular coordinates, you're going to get square roots, which is just undesirable. Yeah. So there's different reasons sometimes. Sometimes we choose polar coordinates for one reason, sometimes we choose it for a different reason. Yeah. Okay, so let's do this in polar coordinates in the sense of, yes, I know there's a pullback domain. Yes, I know there's a stretching factor. We've already computed that. I need to do the slicing. I got to figure the bounds. But let's just not look at that picture over there. Let's think about that slicing process in the XY plane, on the domain that we are given, that we have to look at anyway. Right? Let's save ourselves drawing a new picture. And, well, here's what theta slices look like. Again, they're rays emanating out of the origin. And you can see my first slice is where theta is equal to 0. And my last slice is where theta is equal to pi over 2. Now, if you really want to, we can come over here and say that's exactly what we would have gotten had we been over here in the r theta plane. For whatever reason, you just really got to do that. But let's not. Right? So theta goes from 0 to pi over 2, which I think I wrote down here. Yeah, there we go. So theta, you see, goes from 0 to pi over 2. And then now let's focus on a given theta slice, and let's ask what's the range of values of r. Well, we start there. That's clearly r equals 0. Right? We end here at that point. Well, what is that point? That point is on this curve. That curve, well, that's the unit circle, which has the equation r equals 1. And therefore the upper bound for the r integral is 1. So everything you need to see about the bounds, you can see, you can see from this picture. Okay, so this is what when we say we're doing an integral in polar coordinates, we're saying we're looking in the xy plane and we're going to write down an integral. It's just that we're going to write down an integral with these differentials instead of those differentials, and then we're going to, adapt appropriately, given that in fact what we're really doing is a pullback, right? But we're not drawing that or going to that trouble. Okay. Couple other details. We found the bounds, but don't forget, gosh, this is a big one. Don't forget dx dy. You can't just scratch off dx dy and write dr d theta. Justification being, well, I wanted to be in polar coordinates, therefore I'm just going to declare that dx dy equals dr d theta. Well, that's wildly inappropriate. This is a change of variables. You have to include your stretching factor. Of course you've got to include your stretching factor. So don't forget to put that in there. So easy to forget. It's super easy to forget. You're going to be distracted looking at the domain, thinking about slices and curves and equations to figure out bounds, and in the hustle and bustle, just, oops, I forgot my stretching factor. Right? And it's a tremendously big deal. Right? Because that's what makes this whole process not just symbolic garbage. Right? It's tremendously important. It will count for a lot of points on a question of this sort on the exam. So make ultra sure not to inadvertently forget it. Yeah.
How do you know that R is a stretching factor?
Because we went to this trouble last time. Yeah, we computed that stretching factor, and it's, with our convention that R is never negative, stretching factor is R. Beautiful thing about doing integrals in polar coordinates is you're always using the same change of variables function. It seems silly to say, and therefore the stretching factor is always the same. It's not like it's a magic statement that it's magically always the same. It's always the same function, right? It's always an identical calculation. There is really only one calculation when you're talking about the stretching factor for polar coordinates. So you do it once, you memorize it, and yeah, you don't ever have to do it again. Yeah.
What's the best order for us to integrate with?
Oh yeah, I'm going to get to that. Yeah, absolutely. So give me a minute to get there. Okay, so the other thing to remember is, don't forget you have to translate your integrand into, r's and thetas. Now you can just plug in. Remember, x is r cosine theta, y is r sine theta, and you can plug that in. Or you can also remember that there are these additional formulas. And neat fact: x squared plus y squared is always r squared. Right? But one way or another, you got to plug in for the fact that your integrand has to be converted into polar coordinates, like so. Okay. So I have a suggestion, a memory tool. Two suggestions. So first suggestion: always put d theta on the outside, dr on the inside. And I say always. If I were to go to some great inconvenience, I could probably think of an example where it's more convenient to do it the other way. But it's pretty hard to come up with an example. It just happens to be that most of the time it's a lot easier to think of r as a function of theta than it is to think of theta as a function of r. Most of the time. Right? So, this is in recognition of that fact. Whichever one's on the inside is the one that you're going to have to solve for in terms of the one on the outside. So if it's more convenient to solve for R, put R in a position where you have to solve for it. Right? So almost always better to do it in that order. The other suggestion I have, and I think I really strongly encourage you to do this, think of this as a single thing. Think of that as, well, and rightly so, think of that as being your dA. So forget about polar coordinates for the moment. Why did we write down dx dy? Well, because that's how we represent a little piece of area when we're writing down an integral in rectangular coordinates. Well, in this scenario, what does dx dy look like? What does a little piece of xy area look like? But in terms of r's and thetas, it's r d theta. Right? So don't think of this as step one, I've got to convert x's, dx dy into dr d theta or something. That doesn't make any sense at all. And then subsequently, I'm going to stick this in here because the book says so. Right? That doesn't make any sense at all. That's not a good way to look at it. dx dy is r d theta. So my advice, don't ever write down dr d theta by itself. Write this all down in one stroke. Right? r d theta. That's what you write at the end. If you're going to do an integral in polar coordinates, write down r d theta kind of first, if you will. And then you can't forget that r. Okay. Alrighty. Alright, here's another. Oh, by the way, notice I did that here. r d theta. That's my dx dy. Okay. Now, I started giving this advice quite a few years ago, and then I started noticing a different kind of mistake that students were making. Students were taking me a little too literally when I say that this is a single thing, right? And what they were doing was not then subsequently, once you have your integral in polar coordinates, not then subsequently combining the whole integrand and realizing, in this case, for example, the integrand is r cubed, right? Part of which is from the rectangular integrand, part of which is from the stretching factor. But nevertheless, our integrand is r cubed. There were students that were just kind of scared to let go of that, like they had to leave that there out of deference to the fact that the stretching factor is important, and then they would just do an integral. I mean, they would integrate just the r squared and get like 1/3 r cubed and stuff like that, and that r would just perpetuate, just stick there all the way down the calculation. Well, that doesn't make any sense either, right? I mean, the whole reason we have stretching factors is because they are part of the new integrand that has to participate in the resulting integral. So anyway, don't make that silly mistake either. Okay, what if R is the entire disk? You can think of this as there being a starting slice here where theta is equal to 0, and then theta keeps going around until it ends here at 2 pi. So whenever your domain goes all the way around the origin, 0 to 2 pi are your bounds. Okay, so, right. Okay, all right, here's a couple of weird examples. Let's suppose that you have, as your domain, an annulus. Like that. Inner radius of 1, outer radius of 2. Right, so kind of a moat, if you will, around a castle, something like that. Okay, so how would you deal with this? Well, there's a temptation students have. Some students would like to say, well, I'll do the integral first on the big disk, and then I'll subtract from that the integral on the smaller disk. I'll do green minus blue, and that'll leave the moat. annulus. Okay. Well, you can't always do that. Notice in particular this integrand here. That integrand, 1 over the square root of x squared plus y squared at the origin is undefined. Right? So you can't do either of those integrals. Neither of these disks can you do a double integral, because on the disk, the integrand is not continuous. It's not even defined at the origin. So you can't do that. Rectangular coordinates, you're just in big trouble here. Now again, the obvious, way around that would be to break this up into pieces, and you could, break it up into, that piece and that piece and that piece and that piece, and there's 4 separate pieces, but again, who wants to do that? And that's highly undesirable. Okay. All right, so the idea is to just make a 0 to 2 pi argument, right? So we'll just say that theta starts there at 0, and theta goes all the way around until we end here at 2 pi. And then for any given value of theta, between 0 and 2 pi, r starts there, which is on that curve, which has this equation, and r ends at that point, which is on that curve, which has that equation. And there you go, polar coordinates. Okay. And don't forget, of course, that there's your dA. There's your area element, right? R dr d theta. Don't forget the R. And again, if you write it down like I did here, R dr d theta as a single thing, you kind of can't possibly forget. Don't forget to convert your integrand into polar coordinates, and then look at the happiness that ensues. Those R's cancel, and you have effectively an integral of a constant over a rectangular bound. World's easiest integral. And answer is 2 pi. That's very nice. Okay. All right, here's another kind of a weird example. I think this is a good one to think about. So suppose I look at this spiral defined by this equation here, r equals theta. This is a weird curve. Think about different values of theta. When theta is 0, r is 0. So that gives us this point. As theta increases, right, increasing values of theta, well, r increases. And as we sort of move around and simultaneously get further and further from the origin, we make a spiral. It's a little wacky. Okay. All right. So how do we deal with this? The region that I'm looking at is this is a weird little region. That shape, like that. And notice it's not sort of triangular-like. It's got a little notch taken out of it right there. Right, so how are we going to deal with that? Okay, so here's how we're going to deal with that. We're going to look at this shape, start thinking about what slices look like. Different theta slices all look kind of like... Oh, that's terrible. Let me try that again. Different theta slices all look kind of like this. Right, and they have a lower bound curve. They have an upper bound curve. Trouble is, they're the same curve, so that's a little weird. How do we deal with that? Well, once we set our range of values of theta and say we're starting with theta equal to 0, and we're ending with theta equal to pi over 2. Now that theta is set as between 0 and pi over 2, this lower bound curve remains r equals theta. And that's where that curve came from in the first place. But the upper bound curve isn't. This upper bound curve, there's a temptation to say, well, that's r equals theta too. But that's r equals theta when theta has been allowed to go an extra 2 pi around, an extra full trip around. Right? So for these lower values of theta, it's theta plus 2 pi. Yeah.
Could we just say 5 pi over 4?
Could you say what?
5 pi over 4.
What do you mean 5 pi over 4?
Instead of theta plus 2 pi.
Well, no, because it's a function of theta, right? So theta ranges over all of these different values, right? So we're not interested just in that point. Does that make sense? Yeah. We're interested, and I think maybe you would have meant 5 pi over 2. Yeah. But so we're not just interested in that point. We're interested in how do these values of r move as theta moves from 0 to pi over 2, and whatever the theta is between 0 and pi over 2, going an extra 2 pi around is how you actually get to that point on the curve. Yeah. Right. Okay, so all of that having been noted, here's the bounds. You can see as we agreed, theta goes from 0 to pi over 2. R goes from theta to theta plus 2 pi. Okay. All right. And again, notice I had the presence of mind to write this down in the way that I'm advising RD theta. Because that's a thing, right? RD theta is a meaningful item that represents in the picture that I'm looking at little pieces of area. That's reasonable. And I emphasize in that picture that I've drawn right there, drd theta is not a thing. It doesn't have any meaning in that picture. And there's no reason to write that down on its own. So please always write this down as a group. And then your integrand is R. Okay. Alrighty. So when should you use polar coordinates? It's a tool in your toolbox. Use it when it seems like it might make your life easier in some form or another. It may be that it's because you're looking at your domain, and your domain is going to be something undesirable in rectangular coordinates. Maybe we hit corners. Maybe circles are going to make square roots happen, and it's something like that, right? But if you think your domain's going to be easier, usually that's the best motivation to use polar coordinates. On the other hand, sometimes it may be that there's something weird about your integrand, and the fact that x squared plus y squared has 2 terms in rectangular coordinates, but it only has 1 term. It's just r squared in polar coordinates. Sometimes that might be convenient. That's more rare. Okay, so a couple more just sort of examples of particular little oddities that happen. Suppose we're looking at this domain here. That's a strange little domain, kind of a partly eclipsed moon or something, right? Rectangular coordinates is going to be a bummer. You either have 3 slices like that, or 3 slices like this, right? It's going to be undesirable in rectangular coordinates. But I see that there's circles all over the place, so maybe in polar coordinates this isn't that bad, and it's not hard to persuade yourself that that circle has a really easy equation, right? This circle, well, you've got to do a little bit of polar coordinates work, right? But not hard to persuade yourself that that has that equation. Of course, you get that from what we're given here. Right? And so make sure you remember how to do that conversion from rectangular coordinates equations to polar coordinate equations. Okay. So, slice it up, look at the bound. It's the usual thing. And the thing I wanted to point out on this question is how to find these theta bounds. How do I know what the value of theta is at that point? And one thing you could do is you could write down the equations of these 2 circles and find the points, analytically. But it turns out there's an easier way to do it in this case. I just like pointing at it. Every so often you get lucky, right? So always keep on the lookout for the little bit of good fortune. And here it is in this case. That distance, I point out, is a radius of that circle, which we know is 1. And here's the other thing, though. That distance and that distance, those are both radii of that circle, and therefore we know those also are 1, and therefore I have an equilateral triangle. And therefore this angle that I'm interested in here is clearly pi over 3. Isn't that nice? Every so often you get lucky. Yes?
You can just solve for cosine theta equals 1.
Yeah, you can do it analytically if you'd like. I'm just pointing out that, from the picture, you make a clever observation about distances that that are effectively given in the question, and it just falls in your lap. Yeah, right. Ditto down here, of course, negative pi over 3. Okay, this next example, this is a classical calculation. I think everyone should see this, so I'm going to go through it kind of quickly. I'm not going to show all the details. But first I want to give you a quick comment as to why this example is important. It has to do with this function right here. That function is heavily involved in statistics. Right? If you've ever seen something called a Gaussian distribution, sometimes called a normal distribution. Well, this is the bulk of the algebra in that distribution. There's different versions of it. Integrals of probability density functions calculate probability. So being able to integrate, one of the most important probability density functions in the world is extremely natural to want to do. Right? That's how you compute probability. In particular, if you want to normalize a distribution, you have to do an integral from negative infinity to infinity and divide to make sure that the integrand is 1. The integral is 1. That's how PDFs work. Okay, so it's a big deal. Here's another thing about this function. Unfortunately, you can't write down in the sense that you're going to take this. You can't write down an antiderivative of this function. There is no what they call closed form antiderivative of e to the negative x squared. You just can't do it. Well, look, the way we integrate things is by finding an antiderivative and then plugging into the fundamental theorem of calculus. If you can't find an antiderivative, doesn't that mean we can't integrate this? So this extremely important integral, we are blocked from computing it by our standard means of using the fundamental theorem. So we have a very significant problem here. So let me show you how to compute this thing. This is a lovely, lovely calculation. I don't know if I ever would have had the creative insight to come up with this solution on my own. Like I say, this is a classical calculation from way back. Here's the idea. This integral that I would like to compute, let's give it a name. Let's call it J arbitrarily. First insight is don't compute J directly, compute J squared. So here it is, J squared. You see there's that integral, and then here it is again. Now you might complain and say the one on the right, hey, that's got y's instead of x's. At which point I observe it's a dummy variable. It's going to integrate out. I could replace the y with q. It's still the same function defined on the same domain, and it's the same. It's going to give me the same integral. It's the same Riemann sum, different dummy variable. Who cares? Okay. All right, so here's J squared. First tricky move. This is just a number. So I can freely stick it inside of the y integral. Right? It's not a function of y. Therefore, I can just move it in or out of the integral as I prefer, and I'd like to stick it in there. You'll see why in a moment. Okay. Having done that, this is not a function of x, and I would like to stick that inside of the x integral. Like that. Now again, perfectly legal, right? If it's not a function of x, just stick it right on in there. Like it's a 4. Okay. And then don't forget your algebra 2. Observe that here we have a rectangular integral that goes over the entire plane, all of R2, right? I mean, x goes from 0 to infinity, y goes from 0 to infinity. So this is, in fact, an integral over all of R2. And then the really slick move at this point is let's take this integral and do it in polar coordinates, as it turns out. So here it is in polar coordinates. All right, this is how you describe R2 in polar coordinates. Theta goes all the way around. For each value of theta, R starts at 0 and goes off to infinity. Yeah, that covers all of R2. Convert from rectangular to polar. That's just plugging in. Don't forget, dx dy is RD theta. Again, that R, the stretching factor from this pullback. Don't forget the stretching factor. And it's basically all over at this point. It's it's weird. It seems like we've made the problem even harder because we're computing not just J but J squared, and then furthermore now we're doing it in polar coordinates. Yikes! It keeps getting worse and worse. And now look at our integrand though. Our integrand is now easy. That's an easy substitution. Just let u equal, here looking at this, let me say, let's let u equal to negative r squared. All right, and then du is right there looking at me. And there's a couple of minus signs and halves to keep track of in details. And of course it's an improper integral and you got to write it as a limit. But the big point is that by switching it into polar coordinates, we get this extra r in there that makes substitution possible, and it all falls into place. So anyway, classical calculation, I think that's really cool, and I think everyone should see this at least once in their lives. So there you go. Okay. All right. Okay, so that's polar coordinates. We're going to do cylindrical coordinates now. This is another calculation that everyone should do. So recall, cylindrical coordinates you can think of as a function. You give me an r, a theta, and a z. The cylindrical coordinates function returns an x, a y, and a z, namely a point in xyz space. You can choose to view that as a change of variables function, in which case you can compute the stretching factor. And again, everyone should do this calculation. I did mine. You got to do yours, right? Where you write down all those partial derivatives. Good news, they're not very hard. Take the determinant, and what you'll find is that your stretching factor is the absolute value of r, which is a familiar result. So we make a familiar move. We make a promise to always choose non-negative values of r, in return for which we get to lose the absolute values. It's just like in polar coordinates. No surprise, right? I mean, this is polar coordinates in R3, so no surprise that it ends up working a lot like polar coordinates. Okay, so make sure to memorize this stretching factor, R. Again, when you start slicing things up, you don't have to draw the pullback domain. I mean, here's what you might say, your pullback domain. You don't have to actually draw that, because any slices that you do in the pullback, those slices, I would call those theta slices, for example, because they represent constant values of theta. I can draw those slices right here in XYZ space. Here's that first theta slice where theta equals 0. Here's the next theta slice where theta is some slightly larger value. Here's the next theta slice where theta is yet a little larger. I can draw and see those slices over here in the XYZ space. I don't need to draw them in the pullback. I don't need to draw the pullback space at all. Okay, so same deal. Let's do a couple of examples. I'm not going to spend a lot of time on cylindrical coordinates because spherical coordinates coming up is really more interesting. But here's a first example. Suppose I'm looking at this upper semi-ball, we call it. So it's half of a ball, the upper half of the unit ball, of a ball of radius A. How would I slice this up? Well, again, I could do this rectangular coordinates, in which case square roots everywhere. Massive inconvenience of square roots and integrands, and nobody wants this. So let's think about cylindrical coordinates. There's what a theta slice looks like. Think about how the ball behaves. A slice of a ball is going to look something like that. And I've got to go all the way around. So theta is going to go from 0 to 2 pi, just like in polar coordinates. Okay. All right. Now, we restrict our attention now to that specific theta slice. Next question. What is the range of values of R, let's say? By the way, I'll comment in a minute about the choice of order on the differentials. So, R being next. Well, R slices, constant values of R. Keep in mind, I'm only interested in how they sit inside of this existing theta slice, right? We only look at a slice once you've made a slice. Well, they're just little vertical line segments like that, and R starts at 0 and it ends at, well, that point. What can I say about that point? Well, it's clearly at a radius of the sphere and therefore is A. So R goes from 0 to A. Lastly, for a given theta slice, for a given R slice on the theta slice, range of values of Z. Well, Z starts there, which is clearly 0. Z ends here. Whew, okay, there. What do I know about that? Well, that's on the sphere, which has that equation. Solve for Z. Right, solve for Z there, and our upper bound then for Z is that. That's really, I mean, the slicing process is just it's kind of a curved version of triple integral slicing. It's the same process, really, right? Just got to think about what do constant values of given cylindrical coordinates look like instead of constant values of given rectangular coordinates. Okay. You could instead do this with your differential going in a different order. Here's an example, a different order. We could do our Z slicing first. If you do your Z slicing first, there's your first slice. Successive slices look kind of like that. Your last slice is up there at the sort of the very top. Not hard to see, 0 to A. For a given Z slice, theta slices. Well, oh, I'm sorry, I wanted to switch theta slices go all the way around, so theta goes from 0 to 2 pi. And then, finally, on a theta slice of my Z slice, R clearly starts at 0. R clearly ends on, well, it ends on that point. That point has this equation. We are looking for our R bound. Solve for R in that equation, and you get that as our upper bound. Everybody happy? Okay. All right. Okie dokie. So good news. Of these 6 different choices of how you might slice, right? Turns out there's really only 2 that you ever need. The way to remember what they are is always keep R and theta together and in the order we've already agreed to. In other words, always put dr inside of the d theta and immediately to the inside. And then the only remaining question is dz on the right or is it on the left? Right, so those are the 2 different choices of order that you'll ever need. There are some situations where I suppose you could stick the dz in between there, but it won't buy you anything. So I would encourage you, don't make your life complicated by entertaining confusing list of more numerous possibilities that won't buy you anything. Right, so just stick with these 2 as your options. And again, don't forget your stretching factor. Right? Think of these as single things. These things, r dr d theta dz, r dz dr d theta. Those are your dv's. Those are your dx dy dz's. Okay, so write them down as a whole. Spherical coordinates. It's going to be the same game, different details. Spherical coordinates are a way of keeping track of where you are in space. Okay. They're functions, right? When we think of them as as functions where given a rho, a phi, and a theta, that then defines a point in XYZ space. And if you have a function, you can choose to view it as a change of variables function. So, same pattern as both of the previous coordinate systems. We need to compute the stretching factor once and for all. Again, everyone should do this once in their lives. I did mine. So y'all do yours, right? So now this one's a little annoying. The partial derivatives. There's a bunch of trig that shows up. And there's a little bit of tedium in this. But it's a healthy tedium. Big hint. Pythagorean identities show up and can make your life much simpler on several occasions in this calculation. So don't forget sine squared plus cosine squared is 1. And look for opportunities to take advantage of that. That said, I want everyone to do that calculation. Everyone really should do this at least once in their lives. So please do. Here's what you're going to get. Absolute value rho squared sine phi. Okay. That's another thing to memorize. Make sure to have that memorized. Okay. So here's a common mistake that students make at this point. Very common. Students think, well, look, spherical coordinates is not that different from polar coordinates. Well, okay, let me let that slide for a moment. And therefore, because in polar coordinates, the deal was that we had to always choose non-negative values of r. Well, then by analogy, shouldn't we need to always choose positive values of rho? Lots of students fall for this line of reasoning because, well, rho is kind of like r or something. Well, that doesn't make any actual sense. Let's think it through. What do you benefit if you promise to always choose positive values of rho? And I point out you don't get anything out of that deal because our stretching factor here involves a factor of rho squared. If rho is negative, I don't care. Rho squared is still positive. Rho squared is all that I care about in this formula. So insisting that rho be positive is pointless. Absolutely pointless. So go ahead and choose all the negative rhos you want. Knock yourself out. Doesn't matter. Okay. Here's what you got to worry about, though. You do have to worry about your phis, right? Sine phi can absolutely. We have a threat of the possibility that sine phi might be negative, and that's going to force us to worry about absolute values that we don't want to have to worry about. So forget about some sort of alleged analogy between polar coordinates and spherical coordinates. It's not that good of an analogy anyway, right? What you need to do to get rid of those absolute values is make a choice that makes sine phi always non-negative. And the way you do that is to choose phi always to be between 0 and pi. Then you get to lose the absolute values. And now your stretching factor is just rho squared sine phi. Okay, again with the good news. Those are the values of phi you want to use anyway. Those are the easiest, most natural, first choice values of phi anyway. So again with the win-win, if you promise to do exactly what you wanted to do anyway, then you also get to do this other thing that you wanted to do, namely lose the absolute values. Okay. Alright. It's got nothing to do with rho. Again with the slices, let's look at, here's the theta axis over here in our pullback space. There's a theta slice. What does a theta slice look like over here? Well, it's just a constant value of theta. That's what that looks like. What about phi? Here is the phi axis. Here's what a constant value of phi looks like. Well, in XYZ space, that's a cone. And just think about, in XYZ space, phi is the angle off of the z-axis. And the collection of points whose angle off the z-axis is some fixed value is going to make a cone centered at or vertex at the origin. Yeah.
Is it going to be is there going to be another cone underneath it?
Nope. Because phi is always between 0 and pi. Yeah. There's another convention that most people choose, which is just to make your life easier. to always choose rho to be positive, just because, I mean, why not? We want to choose rho to be positive. Just, it really does make things easier to visualize. And so with the additional convention that rho is positive, which again, I think everybody wants to do that, then no, with rho positive and with this constraint on phi, it's just this up here. Yeah, right. Good question. Okay, and then lastly, rho. Well, a constant value of rho, a rho slice, well, set of points of a constant fixed distance from the origin is a sphere. So the bad news about spherical coordinate integrals is that the slices are weird and curvy and stuff. Here's the good news, really good news, and that is if you just stick with a particular order, if you just stick with theta slices on the outside, phi slices second, rho slices on the inside. If you always do d rho d phi d theta, look at what happens. Your theta slices are flat because, well, that's what theta slices look like. Your phi slices, here, let me, your theta slices are flat. Your phi slices, okay, it's a cone, but I only care about how that cone intersects with my theta slice. And inside of that half plane, it's just a straight line. Right, it's a ray coming out of the origin. Okay, and then it's easy to keep track of rho. Rho is going to have some starting point and some ending point, and who really cares what's happening there anyway? Okay, so the slicing process is very comfortable if you choose that order. So always, for the purposes of Math 212, always do your slicing in that order. Also, never forget your stretching factor. So again, with the single, in a single stroke, write all of this down. Rho squared sine phi d rho d phi d theta. Think of it as a single thing to write down all at once. Don't ever write down d rho d phi d theta by itself. That's weird. Why would you ever do? There's never a need to do that, right? Always make this great big thing with the stretching factor, what you write down. All right, we're out of time. See y'all later. I have homeworks to return, and I also, those of you who came in after I started talking, I make sure I get you on attendance.